Good morning, everyone, and thank you for joining me here at the Collective Intelligence Conference. First, I want to express my sincere gratitude to the program committee for giving me the opportunity to share my work at this fantastic conference. Today, I will present a mathematical analysis of the homepage framework, better known through its celebrated diversity transferability theorem. My goal here is to take a critical but constructive look at the theorem's foundation, its assumptions, and the way simulation results have been interpreted. By examining the mathematics, I hope to clarify what the theorem does and does not tell us about the power of diversity in collective problem solving. So let us start with a little bit of introduction and background. So the idea was to create a model for collective problem solving. The problem is to find the maximum of a given function v that goes from x, which is finite, to the real numbers between 0 and 1. We assume there is a unique maximum, and that is the optimal solution. But more importantly, problem solvers are modeled as functions that go from x to itself. The idea is that they start from a given point, which is like a guess value, and they return what they believe is the best solution, given that they have started from here. So what Hong and Page did was to publish a theorem that essentially it says that under certain conditions, random groups of agents outperform groups of best performing agents. And that's what they call the diversity transferability theorem. And this theorem has had a lot of impact. It has appeared in a lot of places, and it continues to generate active research. So the idea of this presentation and the idea of the paper that this presentation is based on is to mathematically analyze the theorem and the simulations that they use to support the theorem. So let us start with the mathematical theorem. So the theorem can be reduced to the following proposition. So as hypothesis, let us assume that we have a pool of agents such that they do not worsen the situation. That is, if they start from a point, the potential solution that they will return will not worsen the situation. It will non-strictly improve the situation. Let us also assume that there's a unique best agent, and this agent is imperfect. That means that there are points of the space such that this agent will not arrive at the correct and the optimal solution. Finally, let's assume that we can select agents in the way that we want. That is, that we can choose agents until they outperform the best performing agent. And we can do that in part because of point 1. So the thesis, which is trivial, is that this random group will outperform the best performing agent. So this is the basic idea of the homepage theorem, the diversity transferability theorem. And as we can see, there is no mathematics involved here. We don't need mathematics to understand this theorem. And actually, we can, using that pseudo theorem, that idea, we can give a direct and simpler proof of the same theorem that was presented by Home and Page. And to go to that pseudo theorem, they need to assume a set of conditions. These assumptions are as follows. For instance, they have to assume that agents share all the same values. They do not have disagreements. They assume, or it's implied in what they assume, that group deliberation always end up in unanimous agreement. That a trivial corollary of what they assume is that if you have enough agents, you will always find the solution to any problem. And also you need to assume clones. You need to assume that there are an infinite amount of copies of each agent. So what we did in the theorem, in our paper, was to see what happens if you remove one of these hypotheses. And what we saw is that you can create counterexamples if you start removing just one of them. is enough to create a lot of counterexamples. And also, another question is, what happens if we try to make the theorem more realistic? Following that, let us see our alternative result. So we are going to impose a more realistic framework. So for instance, we will allow the possibility of disagreement. We will not assume the existence of clones, and we will also impose a more realistic group selection. That is, we will compare diversity versus ability in a proper way. So here, the diversity group will be such that we impose the minimal loss in ability possible, but we will impose full diversity. And for the ability group, we will impose the same level of ability as before, but we will impose a great reduction in diversity. And given that, what we can prove is that the ability group will outperform the diversity group almost surely. That is with probability 1 or 100%. So that means that minimal changes in the hypothesis of the theorem destroy it. That is, the framework, the theorem is not robust. Let us see what happens with the simulations. So the first thing and the first obvious thing is that there is a huge gap between the simulations, because these simulations are a toy model, a toy framework. There's a huge gap between that and the real world. So the application to the real world of this is not straightforward. But given that, the next thing is that the parameters that appear in the original paper were such that everything worked fine for the random or for the diversity group. So what we are going to do here is to explore what happens if we start changing these parameters, but within the same framework, or what happens if we start changing the framework a little bit, but to make it more realistic. And what we will see is that we will arrive to opposite conclusions. For instance, this is a plot that reflects the situation of the original paper. We have in blue the ability of the random group, and in red the ability of the best performing agents. So as we can see, there is a slightly advantage of the random group over the group formed by the best performing agents. Another aspect is that the theorem and the simulations are not properly connected. First, the theorem hypotheses are not the same as the simulation hypothesis. There are key assumptions that are missing in the simulations, and also the thesis of the theorem is not the same as what we see in the simulation. There are, as we will see later, there are particular aspects that can appear in the simulations, but they do not appear in the mathematical theorem. So the theorem is not useful to understand the simulations. As we said, the claim only holds for a specific choice of parameters. And when we change the parameter, what we saw in the paper is that the diversity transability theorem no longer holds. In particular, if we increase the group size, then it's no longer true that diversity trumps ability. And this is important because it refutes conjecture that Landemore proposed, and sometimes this is called the numbers trump ability theorem. This was to support democracy, but if the framework was truly applicable, it will actually support aristocracy. For instance, let us see an example. There are a lot of cases in the paper, but let us see one example here. In the original paper, they assume that there are 2,000 solutions, 2,000 possible solutions. So agents can rank exactly, and all of them will agree on that ranking, 2,000 solutions. So what happens if we say that there are only, that there are less solutions? Let's say that there are 30 solutions. So the diversity transability claim no longer holds. And we can see it in this table, the best group, the ability of the best group will be greater than the ability of the random or the diversity group. Another example, in the paper, we introduce a new family of parametric functions V that are different from the ones that were studied in the original paper. And for that set of functions, what we see is that the best group, the group formed by the best performing agents, clearly outperforms the random group. And the difference in outperformance is now 10 times higher than the original one. Similarly, we can, instead of changing the parameters, we can change a little bit the framework to make it more realistic. We can allow different algorithms, then ability transdiversity. We can add stopping points, so because they assume that deliberation can take an infinite time, so we can stop it, and it's no longer true that diversity trumps ability. We can also allow disagreement and then ability transdiversity, and we can create a different framework for the algorithms, which better captures ability differences, and then there we can see that ability absolutely outperforms diversity. So the same problem, minimal changes in the framework lead to opposite conclusions. In the original framework, we can study the individual ability, what happens with the ability of the members of each group. And here we have the mean, the minimum ability, and the maximum ability of the members of the group for the random group, and here for the best group. As we can see, the difference in ability is not that much. There is a difference in diversity in the sense of variability of ability. And then when they act as a group, there is a slight advantage of the random group over the best group. But if we model it properly with differences in ability and diversity, here we have more diversity than before in the sense of variability. And here we have less diversity, but more ability. In this new framework, the delta rho framework that we introduced in the paper, the ability of the best group clearly outperforms the ability of the random or diverse group. So far, we have assumed the framework as given. Now let us study the fundamental problems with the framework. We are going to see 4 of the main problems with the framework, and we are going to see it very briefly. But all of this creates a tension because on the one hand, agents are assumed to be irrational. They have unremovable framing effects, but on the other hand, they are assumed to be super rational. For instance, they can rank 2,000 options and all of them will agree on that ranking. And to see it, we are going to consider an example. We have a problem, which is to decide the best climate policy. We will have 100 possible reforms and 2 groups, one of experts, it will be the best performing agents, and other of random graduates that will be the random group. Very briefly, we can prime experts. They will arrive at a different conclusion if they start, if that has any sense, from a different point. Also, we can easily create dynamics. So any group, for instance, a random group of graduates will always find the solution to any problem, no matter how hard. We can also prove that if we rearrange the solutions, we can transform the most difficult problem into a trivial problem. So almost any group will always find the solution just by reordering the solutions. Finally, the heuristics proposed in the original paper are not realistic. For instance, we can easily design situations where if we start from a far from optimal solution, all agents will be able to jump from there to the optimal solution. But if they start from a solution which is almost the optimal solution, we just need, for instance, a Pareto improvement, no agent will be able to go from there to the optimal solution. So again, that's not realistic. To summarize, the mathematical theorem wraps a direct fact that is not really surprising. The simulations are highly dependent on the parameters, so we can go from diversity trumps ability to ability trumps diversity, just tweaking the parameters. The framework has fundamental issues that make it an unrealistic model of actual collective problem solving. All in all, this model seems more like a no-gravity model when we are trying to study the movement of objects, and not just a simplified model with simplifying assumptions as ignoring friction in physics. So I think it's time to rebuild the framework from scratch and create a framework that properly models ability, diversity, and the interaction in group problem solving. Thank you for your attention. It has been a pleasure. Just a reminder that this work is based on the following preprint and that all the code to generate the tables and plots is public and it's available on GitHub and also with an Sphinx documentation. Thank you.